Today, we're diving into a brand new AI that is tackling one of the biggest, most persistent mysteries in our climate models. And it all has to do with the tiny, invisible particles that are floating in the air all around us, right now. Okay, so let's zoom all the way out and start with the big picture. When you look at images of Earth from space, you see our atmosphere, right? This incredibly thin, fragile layer. And when I say thin, I mean it. 99% of its entire mass is packed into a layer less than 50 kilometers thick. Understanding the complex chemistry happening inside this delicate veil is without a doubt one of the most critical scientific challenges of our time. And, a huge part of that challenge actually comes down to a tiny problem, literally. We're talking about something so small and so chaotic that it has been notoriously difficult for scientists to pin down and predict. I'm talking about aerosol particles. These are the microscopic bits of dust, soot, sea salt, and liquid droplets just hanging out in the air. Now, they might seem insignificant, but they are a massive source of uncertainty in our climate models. And here's the bottom line. If we don't understand aerosols, we just don't fully understand our climate. It's that simple. So, what makes them so tricky? Well, aerosols kind of have this dual personality. On one hand, they directly mess with Earth's temperature by either scattering sunlight back into space, which cools things down, or absorbing it, which heats things up. But on the other hand, they also act as these little seeds that clouds form around. This changes how bright and reflective clouds are and even how long they stick around. It's a really complex two-front problem. And here's the real kicker. Every single one of these aerosol particles can be totally different. Different size, different shape, different chemical makeup. This incredible diversity, what scientists call particle-to-particle variability, is what makes them an absolute nightmare to simulate with any real accuracy. So, you might be asking, how have we been trying to solve this puzzle until now? Well, for the most part, with what you could call a brute force approach. Let's take a look at what that actually means. The best models we have right now do something that sounds pretty straightforward, but is just mind-bogglingly complex. They literally track the life story of every single particle. The whole idea is to capture all that wild diversity we just talked about by simulating each and every particle one by one. And when I say every particle, I really mean it. We are talking about tracking anywhere from 10,000 to a full million individual particles in just one simulation run. You can probably imagine this is, to put it mildly, computationally expensive. It takes a colossal amount of computer power and a whole lot of time. But what if there was a better way? What if we could develop a strategy that works smarter, not just harder? Well, this is where a brand new AI-powered solution enters the picture. Yeah, instead of just throwing more and more computing power at this problem, a team of researchers came up with a completely different way of thinking about it. It's called GLAD, and that stands for Graph-Based Learning of Aerosol Dynamics. GLAD uses a really interesting type of AI called a graph neural network, or GNN. And here's the game-changing difference. Instead of just tracking particles, GLAD actually learns the fundamental rules of how they behave and interact with each other. Let me put it another way to make it super clear. The old brute force method, that's like trying to keep track of every single person in a massive crowded stadium. The new GLADE method is like understanding the general rules of how crowds behave, how a wave gets started or how people flow towards an exit. It's a much, much more efficient way to get to the same or maybe even a better understanding. Okay, so how in the world does an AI actually learn these rules of physics and chemistry? It sounds like science fiction, right? Well, let's take a little peek inside the mind of the machine. All right, I know what you're thinking. This diagram looks incredibly complicated, but don't worry, we're not going to get lost in the weeds. The entire process, believe it or not, boils down to a really elegant and simple three-step logic. Here we go. Step 1 is encode. The AI takes all the different aerosol particles and turns them into a network, kind of like a social network. Each particle is a person, or a node, and the connections between them, the edges, represent how chemically similar they are. Step 2 is process. Now this is where the magic really happens. The AI starts passing messages back and forth between all the connected particles, learning their complex relationships and figuring out the unwritten rules of how they're all going to interact. And finally, step 3, decode. The AI takes everything it just learned from that conversation and translates it back into solid predictions about how each particle is going to change in the very next instant.
So, once GLAD has been trained by running through that encode, process, decode loop over and over, it becomes this incredibly powerful new kind of simulator. It can take a snapshot of the atmosphere at one point in time, predict the next step, then use that new prediction as the starting point to predict the step after that, and so on, building a complete picture of the future step by step. So, we have this amazing new tool. It's a huge technical achievement. But what does a breakthrough like this actually mean for us and for the future of climate science? Well, it really all comes down to efficiency and accuracy. With the traditional models, you get high accuracy, but it comes at an extremely high computational cost. GLAD offers a new path to simulations that are not only way faster and more efficient, but can also maintain an impressive level of accuracy. So why does that matter? Well, having a faster, more accurate simulator could kick off a domino effect of breakthroughs. It means getting a much better handle on those big uncertainties in our climate change models. It could lead to more accurate day-to-day weather forecasts. It could give us much better predictions for air quality in our cities. And what's really fascinating is it would let us run the huge number of simulations needed to train even more powerful and sophisticated AI models down the road. So what this all really means is that by teaching a machine to speak the language of these tiny particle interactions, we can dramatically speed up our own understanding of the atmosphere as a whole system. It's a huge leap forward. And it really leaves you with this one big provocative thought. We're just starting to scratch the surface of what these new kinds of AI can do. So you have to wonder, could teaching an AI to think in networks, to see the world not as individual objects, but as a web of relationships and interactions, be the very key we need to finally unlock our climate's biggest and most complicated secrets?